In this video, I'm going to explain what mutation testing is, why it represents a better metric than code coverage, and what the goals and mechanics behind this practice are, with some language agnostic examples. Hi, I'm Andy from Narcolepsy Pumpkin. If you've been here before, then welcome back. If you haven't, then a warm welcome. In layman's terms, the aim of mutation testing is to check if you can logically change the behaviour of a piece of code without any of the unit tests failing. If this is indeed the case, then you've got what is considered a surviving mutant version of your application, and this is a bad thing. If, however, one or more unit tests fail, then this mutant is considered killed.
Test wins fatality.
So how do we make sure our test suite is capable of killing off these mutations in code behavior? We start by going through the code line by line and changing those lines so they're logically different, creating a mutated version. We then rerun the test suite to see if one or more unit tests fail. If one or more tests do fail, then that mutant is considered killed. And that means the test suite actually protects against that particular type of mutation. And this is where you actually find out the scary thing. It's actually possible to have a code base with 100% code coverage, where you make logical changes in the code and the tests don't fail because they don't actually cover all the behavior. The tests have just been written to do enough to get code coverage. If you'd like to learn a bit more about why code coverage might not be something you want to chase, then I would suggest checking out this video up here. And don't worry, you can go watch that now and I'll still be here when you get back. So just to recap, all code coverage tells us on its own is that the code is in fact run when the test suite executes. Now this is a really good first step. The aim of a test suite, however, is to assert the code's intended behavior. All code mutations are changes, but not all changes to the code are mutations. You should in fact be able to change the implementation or restructure a piece of code without any of the unit tests failing, because those unit tests are there to make sure the behavior is asserted, not the implementation. Mutation testing helps us build a more reliable and robust test suite that in fact supports that level of comfortable refactoring. So what are the goals of mutation testing and how exactly do we measure it? So firstly, the aim is to find weakness within the test suite. And that's weakly tested code, for instance, code that can be logically changed, but is not detected by the test suite. And to find weak tests, those that never catch or kill any mutations. These can often be tests that aren't asserting anything, or tests that don't have a valuable assert. It could also be the dreaded tests that only test code, i.e. no production code is ever run as part of that test. How many times can you get test into one sentence? To give us a measure of this, we can in fact compute a mutation score. If we take the number of mutants that were killed and divide that by the number of mutants created, that gives us our mutant score. Obviously the ideal score in this case is 1, i.e. 100% of the mutated lines of code were killed by the test suite. For example, if we introduced 100 different mutations and 99 of those were actually killed by one or more failing test, then our mutation score would be 99%. So, how does this actually work? There are several types of mutation we can inflict on a code base. The simplest is to change the logical flow. So let's take a really simple pseudocode example. So if we, for instance, let's actually choose a pen. If we say if, let's say A and B, and then we're going to say C equals 1, else C equals 0. Now, how we can change that statement logically, the easiest way is to change its flow. So if we change this and for or, this represents a logical mutation, i.e. we've changed how this branching gets to this line and how it gets to this line in some scenarios. Now I just want to look at this example inside an IDE. So this is C#, and I know these examples I've promised as being agnostic. So I've written two tests, one that takes A and B as being true, and we're expecting a result C from that, which is an integer, and we're asserting that that equals 1 in this scenario. And then for test case 2, we're saying A and B are both false, running the same function and asserting that C is 0. So a simplified version of that code, A and B return 1, otherwise it's going to return 0. Okay, so I've got 100% code coverage here. So all the lines of code in this are actually run by the test suite. And these tests are currently passing. Example of that mutation is in fact changing this to OR. So that's saying if A or B return 1, otherwise return 0. Not changed the unit tests, just mutated the code. If I run all these tests, they both still pass. It hasn't killed that mutation. And if I check, just to confirm, I have 100% code coverage. Now that's a simplistic example, but it tells you exactly why 100% code coverage doesn't necessarily mean you're covering the behavior of the code. And in this case, we are asserting things. It just means that there should be more tests around this function to assert its true behavior in all scenarios. For a test to kill the mutant in that example, it has to fulfill 3 main criteria. The first one being that the piece of code is actually run when the test runs. Now we've asserted that we have 100% code coverage. That test ran that line of code. And obviously, if the test didn't run the line of code, that mutant would by default survive. The second criteria you've got to meet to kill a test with a unit test is it has to infect that piece of code with some state that will cause it to run differently given the mutation, i.e. differently from the original piece of code. In our 2 test examples, that criteria was the one that wasn't met. It didn't actually matter whether it was an AND or an OR, because logically the result was the same given the inputs we'd infected that piece of code with, i.e. the state we inject into the test has to be capable of causing a different flow. This is where triangulation comes in, and having more than one test trying a piece of code from different angles, which gives you a different result. The third criteria is that the output is actually surfaced in a way that the test can assert its value, i.e. we're asserting that C equals a value, which is what we did in the example, or we're asserting that something that is based on that result of C is a specific value. Another example of getting this wrong would be asserting that C doesn't equal 3 in this scenario. That would allow both those tests to pass, but would allow for a lot more mutation within the code flow. So to give a specific example of that based on our previous scenario, if we passed in A as true and B as false, now that meets the criteria that would be a different flow for the AND or OR scenario. But if the assert was either removed completely or that assert is changed to the as aforementioned not equal to 3, then it doesn't matter again what you do with that, the code will pass and the mutant will survive.
Mutant Wins. Fatality.
Just quickly going back to our C# example, just to reaffirm what we're talking about here. If I copy that first test and we say it's test 3, we make A and B different, so we make A true and B false. Now that meets the criteria for having a differing thing. So that and a raw will give a different result. So if true, so we'll put this back to the original state. So A and B equals 1, 0. In this scenario, they're not the same. Therefore, we want 0. So again, if we run this test suite, we should now have 3 tests running and passing. Absolutely. We can now cover unit tests. Still 100%. If we change this to or, run the tests, didn't survive. So that test has, test 3 has killed that mutation. So putting that back to and did everything runs. If we said that this was not equal to 3, as mentioned, all the tests pass. We mutate the code, run the tests again, and they all pass again. That's because this assert isn't sensible. It doesn't add value. In fact, that's exactly the same as just removing the assert. There are several different methods for mutating the code, and that could be as simple as removing a line of code, removing a method body entirely, or making it return a static value. We could also change arithmetic operations, so changing plus for a minus, changing divide for multiply, or vice versa. And we can invert Boolean statements, so saying not equal to instead of equal to, so on, so forth. So hopefully by this point you've got a pretty good idea of what mutation testing is. And you're probably thinking that going through every single line of code in your code base and changing it logically and rerunning the test suite manually would take forever. And I absolutely agree. It would take you forever. But luckily there are a number of mutation testing tools and frameworks available for a multitude of languages. For Java, there's Pit. For C#, JavaScript and Scala, there's Striker. And for Python, there's MutPy. Make sure you check out the links in this description below to all these frameworks and tools. And bear in mind, using a quick search, you'll be able to find a tool for your language and one that fits into whatever your build or pipeline process is. If you've got any questions on unit testing or mutation testing, please stick them in the comments below and I will do my best to give you an answer. If you've enjoyed this video, then please let YouTube know by clicking on like. If you'd like to hear more from me, then please click on subscribe and click on the bell to get notifications.